I love when the story I'm reading tells me what the characters are physically experiencing when they go outside. Like, Anne Leckie will really let you know that the characters are trekking across a frozen wasteland or that the pilgrimage site is in the middle of a swamp. Susanna Clarke has Piranesi spend pages describing the internal climates of a vast marble palace and what it means to survive there. And I think Kim Stanley Robinson would have just dropped the plot and characters altogether and talked about the weather and geology on Mars if his editors had let him. And this feels like it provides a way richer picture of what it's actually like to inhabit these other worlds on a daily basis. Knowing what the ambient environment tends to feel like provides a kind of immersion that's totally unrelated to characters' rich internal narrative or the dynamics of a thousand noble houses or anything else the writer is doing. And obviously, not every author needs to spell out all the details of the climate. Genevieve Cogman in the Invisible Library novels is a British author writing about a parallel London, so she can kind of just say it's London but with worse air quality, and we can kind of figure it out from there. But the further the world of the story gets from the real world, the more it helps to understand the actual physical environment that the characters are standing in. In the context of the kind of world building someone might want to be using a fantasy map generator for, climate is also relevant to a lot of macro considerations beyond being able to vividly describe what the characters might be experiencing. Like, here's a map I've just generated using the newest updated version of terrain generation, and there's no information on this map other than elevation and sea level. What's the climate like in the area I've circled? If it's extremely arid and hot in the summer and cold in the winter, that probably means it's sparsely inhabited and maybe it has long distance trade in relatively lightweight but valuable items. You might think that if there's anything supernatural here, it's something more inhuman, like a dragon setting up in a remote place where it doesn't have to worry about requirements like food and water. Conversely, if it's less arid and more consistently temperate year round, then it might be more densely populated, with some larger settlements and maybe some well established travel routes between them. Supernatural situations here might be witches, or curses that disrupt the harvest, or the favorite of pretty much every settled agrarian society in the world, a thing that looks just like one of your loved ones, that's taken their place, and it's actually evil. Anyway, climate is going to affect the way the map looks, but it's also going to affect the kind of fantasy stories told in the setting. And that's something we'd like to be able to address with this map generator. So, how are we going to tackle this? For most of the video, we're going to be using real-world data to build a very simple climate model based on a very small set of variables. As always, the goal here is not a deep and meaningful understanding of the underlying geophysics and atmospheric dynamics. We're just trying to build something that's going to give us plausible and realistic variety that you could base a fantasy map on. Then, we'll use that very simple statistical model of the real-world climate on some maps we've generated and see what kind of patterns it gives us. And finally, as a preview of what we'll be doing with all this new detail, we're going to add areas of permanent ice to the map where our climate model tells us they could plausibly form. Anyway, welcome to another episode of Multiversal Map Room, where we make fantasy map generation software 1 week at a time with the help of Python, linear algebra, and energy drinks. This week, we're adding climate norms to the map. So our starting point here is going to be real-world climate data. As always, the goal isn't hyper-realistic models of the actual underlying processes because those are way beyond the scope of this project and also because we don't need them. Real-world climate models are extremely cool, but they're not necessary whatsoever to build the kind of fantasy maps we're working on. We're just going to use very basic statistical methods on real-world climate data to ensure that we get interesting and plausible variation in the outputs. So, what does that look like? As a start, we have climate data for 1,854 locations, all of which are weather stations in cities with at least a couple decades of data. These stations generally track a lot of climate-related measurements, but for our purposes, we'll just care about 3. The average temperature in the hottest month of the year, the average temperature in the coldest month of the year, and the total precipitation over the course of the year. As you can see, the locations are pretty well spread out across the planet, with a good range of temperatures and precipitation levels. Insofar as we want a simple but reasonable model connecting terrain to climate norms, this is a sufficiently large and varied data set to start with. To build a simple statistical model, we're going to focus on just 3 inputs. In particular, we care about the latitude, the elevation, and the distance to the nearest ocean. Hopefully it makes sense why these 3 variables feel like they'd be really salient to building models of climate norms, and also why they offer enough variety to give us an interesting climate map when we apply them to the type of terrain we've generated. Incidentally, finding elevation data for the whole world at high enough resolution that it felt accurate and precise, but low enough resolution that it would load on my laptop, actually ended up being a challenge. It's cool how we really have access to so much data now. I'm also going to be incorporating some information about the altitude upwind and downwind, because that turns out to have a pretty big impact, especially on precipitation. But once we have elevation data, adding that is easy. And we actually have pretty decent coverage here. Weather stations are obviously more likely to be on the coast and not at extremely high latitudes or altitudes, but we have good coverage for a realistic range we could probably care about. This data set does skew heavily towards richer countries, and so I was a little worried we wouldn't have enough data for latitudes near the equator, but it doesn't look like that's going to be a problem. Even if the weather stations are clustered at lower altitudes and closer distances to the ocean, we still have decent coverage even above 2 kilometers inland and more than 2,000 kilometers inland. And I went and fed the statistical models, and it turns out that building models of high and low temperature is actually relatively straightforward. Altitude and latitude really matter more than anything else, and so we can quickly get a statistical model that correctly predicts 70 to 80% of the variation in the temperatures during the hottest and coldest months. These models aren't perfect. They miss coastal communities in places like Namibia and Norway, where strong ocean currents give different climates than you'd expect, but we absolutely do get close enough to give us rich and interesting, but also somewhat grounded variation in climate for the purposes of this map generation project. On the other hand, precipitation ends up being a whole lot harder to model. I've spent quite a lot of effort trying to get a decent statistical model here, and ended up throwing in the high and low temperature months as inputs to the precipitation model, but we end up only matching a little more than half the variation. It turns out that things like prevailing winds that don't uniformly blow east-west and the Hadley cells around the tropics have a major impact on precipitation. Also, the range in precipitation levels is massive. Some places get basically none, others get 4,000 millimeters a year. So the basic statistical model I've built here isn't as close of a fit to reality, unfortunately. And to emphasize, obviously we don't need to fully accurately capture the relationship between terrain and precipitation in our models. The goal here is interesting fantasy maps, not precise accounting for fluid dynamics. We want something that looks good and broadly accords with intuition. So I think this is fine for now. But if we start building hydrology and it all looks too plain and repetitive, maybe this is something I'll need to rework down the line. Anyway, how do we translate these statistical models to the terrain we're generating? We need 3 pieces of calibration: how we're handling altitude, how we're handling latitude, and how we're handling distance conversions. The altitude mapping is hopefully really straightforward. We just want the terrain on the map to have a similar range of elevations to the real world. Latitude mapping is just the range of climates we want to include on the map. If the whole setting is meant to be kind of subtropical, you can assert that the whole map just has a latitude between 28 and 32 degrees. However, just because you've specified a really small range of latitudes to pin down the climate, that doesn't necessarily mean that the map is small. So you can also specify the resolution of the map in pixels per kilometer, which lets us calculate, for example, how far inland pixels are. Here's some sample parameters I'm about to use to generate a climate layer for this map. We're going for a fairly high resolution map where each pixel is only 1 kilometer. We're studying that the highest mountain is 2 kilometers above sea level, and we're going for subtropical latitudes throughout. And like in universe, in the world the map is representing, of course you could describe distances as being much further, and the mountains as being way higher. But the climate variables are going to be generated according to this resolution and altitude and latitude, if that makes sense. And here's what the model says for the temperature during the hottest part of the year. Unsurprisingly, this map generates some pretty hot summers, especially in those nearly tropical lowlands close to the ocean in the southeastern part of the map. But there's enough range and elevation that the highlands have relatively mild summers. And at the other end of the scale, here's the temperature during the coldest month of the year. And note that these aren't just palette swap versions of the same map. For example, those lowlands in the southeast had very hot summers, but they don't have the warmest winters on the map. Overall, we've ended up with areas that are consistently warm year-round, areas with hot summers and cold winters, and areas that have a very mild climate. And that's the kind of realistic variation we want to see in temperature, so I'm pretty happy with how these have turned out. Precipitation, meanwhile, looks a lot less smooth because the upwind and downwind elevation matters so much more, as does coastal proximity. We end up with a few areas of very high rainfall along the north-facing coast of that southern landmass, and we end up with a rain shadow in the southeast, and of course the high elevated areas are on average a little bit drier. So if we think back to that circle from the beginning of the video, what's happening there in terms of climate? It's this hilly region with warm summers, cool but not cold subtropical winters, and moderate precipitation that decreases as you increase in altitude, according to our model. And in the real world, this is the kind of climate you'd expect in Portugal or in Galicia in northern Spain. And knowing that climate is going to provide context for what the sensation of being outdoors would feel like, what the passage of seasons would look like, and what kind of economic activities and supernatural forces might make sense here. Anyway, let's try another terrain map. This one has a deep depression in the north that goes way below sea level, some large offshore islands, and mountain ranges that rise up steeply from the ocean, especially in the north. Same underlying algorithm, just a different seed value, and hopefully one that will give us some interesting variation in the climate map. This time, I've drawn a circle around a large, low-lying offshore island that kind of looks like a melted hourglass. What's the climate going to look like there? In terms of calibration, for this one, I'm going to zoom out a little so that a pixel is 2.5 kilometers, and say that the highest altitude is still 2 kilometers, but now we're at a somewhat more northern altitude, going from temperate in the south to subarctic in the north. Again, setting pixel size really just means that the model starts considering land to be inland and pixels to be the relevant upwind and downwind locations for the elevation calculations. It doesn't actually pin down the size of the world we've built. And throughout, I'm showing examples where north is up and south is down, because that's what most maps we see on a daily basis look like. But you can absolutely enter negative latitudes and get the correct behavior of more negative latitudes, meaning more Antarctic and colder. Unsurprisingly, because we're at a higher latitude, and because we're treating pixels as larger surface areas, more of this map is inland subarctic areas where the temperatures don't really get hot even in the summer. The coastal lowlands get warm weather, and so does that big depression, but that plateau in the far north never gets warm even in the middle of summer. Meanwhile, the coldest month of the year does go below freezing pretty much everywhere on the map. It's extremely cold in those northern elevated areas, a little warmer in that big depression, and milder along the coast. The precipitation map here is really busy because this particular map has so much variation in terrain, especially up north. And again, the precipitation model really relies heavily on the altitude of points upwind and downwind. So when you have a big depression close to the ocean, the side of the depression that faces the prevailing winds ends up being really rainy. Meanwhile, the mountains in the far north have almost no precipitation whatsoever. So, what's going on with those islands? They have a mild summer, a winter that's just below freezing, and moderate amounts of rain considering they're facing a big ocean like this. The low altitude means that they just don't pick up as much precipitation as like a higher elevation landmass would. The climate here would be similar to the Aleutian Islands or maybe the low-lying parts of Tierra del Fuego. And finally, because this second example is at way higher latitudes, it has something the first one didn't, namely, areas where it's always extremely cold. I've gone ahead and shown the area up north that would likely be covered by glaciers in white. These areas barely get any precipitation according to our climate model, but they also never really get hot enough to melt, and so this is where you would expect persistent glaciation. The ability to add persistent ice like this is cool for world building reasons. What kind of societies would exist around the edges of an ice cap, but also for storytelling reasons. Maybe there's something frozen under there, and the antagonist is trying to get to it, so our heroes have to stop them. And obviously, having some glaciation on the map isn't the full extent of what we can start doing for biomes. Having these climate norms means that we can start placing forests and fields and deserts, and maybe even more arcane biomes further down the line. But all of that is going to need to wait until a future week after we have a sense of how we're placing things like lakes and rivers. Anyway, that's all for this week. As always, I'm grateful for feedback and suggestions, so don't hesitate to leave a reply. Thanks for watching all the way to the end, and I'll see you next time.